Hello everyone, welcome to a fresh new lecture on the topic Multirate Signal Processing 2, which is a continuation of the topic Multirate Signal Processing 1. I am Dr. Anirban Dasgupta and let's get started. So, we will start today's topic with half band filters. So, what are half band filters? So, when interpolating a signal, the interpolation filter will in general alter the samples of the signal x of n in addition to filling the zeros. Sounds complicated? Let us see. So, suppose we have a signal, so this value is 2, say this value is 3 at index 1 and say this value is 2.5 at index 2. Now, this is my original signal x of n. Now, what we will do is we will first upsample the signal say by a factor of 2. What does it mean? So, I will insert a 0 in between. So, my 0th index will be 2, my second index will be 3 and my index 4 will be 2.5 and I have two more values which are zeros at index 1 and 3 and this is upsampling. Now, we need to interpolate so that these zeros are removed and for that we will use an low pass filter which I have already discussed in the last class. So, let me use a separate color, say let me use this green color. So, what this interpolation filter will do, this will create something like this probably and these are the new interpolated values. Now, you can see that although this is a smoother curve, the green curve, but these original values of x n is distorted. In the new interpolated signal, my resulting values are quite different from the original values. So, the question is, can I design a filter h of n such that, let me use another color maybe blue, such that my original values of the signal should be intact and the other values can be anything, does not really matter, something like this. So, I get a smoother version, I get a low passed version, but in this interpolated signal my original signal values, that is 2, 3 and 2.5, they are intact. So, such a filter which will keep these original signal values intact after interpolation is called a half band filter. So, this is the question, that can I design an interpolation filter which can preserve the original samples x n. So, when I am doing this upsampling by 2, so what should be the condition? The condition is that y of 2 n should be equals to x n, that is even after the interpolation. Of course, after upsampling the samples will remain the same levels, or in general y of 2 n plus n naught equals to x n. Why n naught? Because if this is a 0 centered filter, it will not be a causal filter. So, to make it causal, I will give a shift of n naught. So, let us see what this filter will look like. So, this filter h of n will be a half band filter if will not change the samples of x of n, or if it is centered at n naught, the criteria should be that h of n should be 1 for n equals to n naught and 0 for n equals to n naught plus all the even indices of n. Now, this is very much similar to the delta function and this is the relation that h of 2 n plus n naught is delta n, but does not mean that it is a delta function. This is just for the even values of n. However, you are free to choose any value of h of n for the odd indices. Let us take an example. So, here n naught is 10, that is it is centered at 10. By the structure it is looking like a sink filter. Sink means it will have a box like structure in the Fourier domain. So, if this is my filter in the time domain, so it will be, this is in time, so in frequency it will be a box filter, kind of an ideal filter. However, because of this finite length we have truncated it, and this is a half band filter. Why? Because if you see, so this is having a value of 1, that is at n naught, and the other even indices, that is n naught plus 2, n naught plus 4, n naught plus 6, n naught plus 8, or if you see this side n naught minus 2, minus 4, minus 6, minus 8, these are all zeros, and remaining are kind of looking like a sink. And again, if it is a 0 centered, this is the condition, although this will not be a causal filter, then it will be depending on the future values of the input, and then for that you cannot go for real time processing, you have to do offline processing. Okay. So, if the idea for a factor of 2 is clear, let us extend this for a factor L. So, when we extend this for a factor of L, such kind of half band filters are called Nyquist L filters, and this is the general criteria or the general condition for a 0 centered Nyquist L filter, that h of Ln, where L is the factor by which we are upsampling, equals to delta n. If you look at this graph, so this is a Nyquist 4 filter which is centered at n equals to 15. So, at n equals to 15 you see the value is 1, and since this is a Nyquist 4 filter, so after every 4 values you will get a 0, like 1, 2, 3, then fourth value is a 0, 1, 2, 3, fourth value is a 0, this side 1, 2, 3, fourth value is a 0. So, what next after Nyquist filters? We will come up with some interesting identities. And what do you mean by identities? So, these are similar in both ways, like we have the convolution multiplication identity. So, in time domain when we do convolution, in frequency we get a multiplication and vice versa. So, these are called noble identities. I do not know why they are called noble, but let us try to understand why these identities were made in the first place. So, if you see this structure, what is this? This is an interpolator. So, we first upsample by a factor L, and then we use the filter to remove the spectral images. Of course, if you are feeling this difficult, you should go and watch the previous lecture, multirate signal processing 1, because this is a continuation of that. Okay. So, what is the problem in this? The problem is that this filter is operating at a higher sampling rate. So, if my input signal was say sample at 100 hertz, this is, and if say the value of L is 5, then this filter will operate at 500 hertz. Now, if a filter is operating at a higher sampling rate, then the cost of the filter will be higher, because you need costlier components. But there is one more factor which I will discuss soon, but as of now consider that this filter will be costlier because I have to work on this at a higher sampling rate. So, can I somehow bring this to a lower sampling rate? Well, the only way by which we can bring it to the left of this upsampler is to place it before it. But will it be the same filter? Definitely not, because now the sampling rate will be less, L fold less. So, here if you see that if this filter response is h of z power L, then this filter in the noble identity will be just h of z, which effectively means that if I do the convolution first and then an upsampling, this is equivalent to individually upsampling both the filter and the signal and then doing the convolution. There is also a similar identity for the downsampler. So, here if you see, So, this is our downsampler. This we have a pre-aliasing or anti-aliasing filter. So, this is again operating at higher rate, m times higher sampling rate. So, if we bring this after the downsampler, definitely the sampling rate will reduce, and here we will see that this is having h of z if the previous sampling rate was h of z power m, not sampling rate, but the impulse response, the pulse transfer function of the system. So, this is equivalent to convolving h of n, which is this case, with a downsampled version of my signal is equivalent to downsampling the convolution of the signal with the upsampled version of the filter. This is the upsampled version of the filter. So, we are first convolving with the upsampled version of the filter and then we are downsampling it. Now, these identities will be useful in the subsequent concepts, which is polyphase decomposition. Now, polyphase decomposition is an interesting concept, and we will use these polyphase decomposition and the noble identities to create something very new and efficient way of implementing a filter. So, first step is I will decompose this x of n into two sets, even and odd samples. Does this sound familiar? So, we did something similar in the FFT derivation. So, now we have x 0 of n, which are the even samples of x n, and x 1 of n, which are the odd samples of x n. Now, if you do the z transform, we see that x of z will be x naught of z square. Why x naught of z square? Because x naught is operating at how much? Twice or half the operating frequency. It is operating at half the sampling frequency as x of 2n. So, if we do the reverse, that if we do in terms of x, so x will be here x naught z square, and this will also be x 1 z square, and this will appear as a delay. So, you just change the sides and see. So, this will be the relationship. Let us take an example to clarify the concept. So, this is our signal and this is my 0 index. So, let us take the odd indices or odd values of the signal first to form x 0 n, which is 3, 5, 2 and minus 3. And similarly, x 1 will be formed by 1, 6, 4 and 7. This is simple. Now, if I do the z transform of the original signal, this is what I get from this, and this is just if I plug in the equation of z transform. And if I get the z transform of x naught n, I will get this, and for x 1 n, I will get this. So, you can verify the relation which I just explained in the previous slide, this one. So, just plug in and you will check that this is verified. So, this is the block diagram in time domain, where we are downsampling the signal x n by 2 and also a shifted version of the signal. This is typically an advance, this is z. If you take z inverse, it will be a delayed version, and I am downsampling by 2 and I get x 1 of n. And these are the two signals which I have already explained. So, we will extend this concept for a factor of 2 to a factor of m. And what happens here is, so here I see that I get m such components x 0 n to x m minus 1. Like if I have say 1, 2, 3, 4, 5, 6 and I want 3 phase. So, 1 and 4 will be my x 0, 2 and 5 will be my x 1, 3 and 6 will be my x 2. This is also very much similar to the divide and conquer FFT. So, here I have 3 components. Now, I will divide them similarly in this manner. So, this overall x of z is divided into smaller Z transforms. So, the polyphase is an inherent implementation or application of this downsampling. Let us try to understand an inherent implementation of upsampling or interpolation. And here we will use the noble identities as well as the polyphase decomposition to obtain efficient structure. And this is what I was talking about, that what is the use in changing the order of the upsampler and the filter. So, this upsampler is followed by a filter in an interpolation system, this you know. Okay. What the upsampler does? It is inserting zeros in between samples. Like if I have a sample say of size 2, length 2 or amplitude 2, which is 3, say this is 5. So, upsamplers, if I upsample by 3, so I am inserting 2 zeros here. If I upsample by L, I insert L minus 1 zeros. Now, after that if I am doing the filtering H of n, what I am doing? I am convolving this with this sequence, upsampled sequence, that is x of n by 3 you can say. And now technically you know that what is the complexity of convolution, but here I am unnecessarily multiplying a lot of samples with zeros and doing a lot of addition with zeros, which is technically useless and baseless. Although these are required, but we are wasting some resources. That is, in other words, what I said, that this is operating at a higher sampling rate, but this high sampling rate is mainly consisting of lot of samples which are zeros. That is, most of the samples to the input are 0 and the filter is operating at a higher rate. So, can we do better? And that brings to the concept of efficient implementation. So, we can use the polyphase representation and then use the noble identities. For example, this is my signal, I upsample by a factor 2 and then I do the filtering to remove the spectral copies to get my output yn. Again, this h of z can be written as a polyphase decomposition, and here since the upsampling is by a factor 2, I will just do 2 terms h0 and h1. Next, what I do, since this is addition, so I can say that this is a parallel structure, that this h0 and h1. And why parallel? Because this is being decimated in time. So, this is half of the components which are the even samples and these are the odd samples, or whatever, these are the odd samples, these are the even samples, and these two gets parallelly convolved. So, this is once doing a parallel computation, so it will be faster, that is fine. Now, what is the problem? This is operating at twice the sampling rate. Of course, the same thing is happening here, but how to solve this issue? Let us see. So, now if I just bring this upsampler to each block like this, the same thing, just I have brought the upsampler before each block separately. And why I did? Again, in this step I just cascaded this because this is a product in Z, so I can cascade the Z inverse here. And now with this I can now implement the noble identities, which says that if I can bring this h before, and this h is a function of z square, if it comes before the upsampler, it becomes a function h of z, and same for here, and this was the whole purpose. And now we see that h0 and h1 is operating at lower sampling rate, that is a sampling rate of x of n, and this is an efficient implementation of interpolation. Now, extending this concept, we can form something called digital filter banks, and these are immensely useful in many cases, like even in the construction of discrete wavelet transforms. So, what is a digital filter bank? It is a collection of band pass filters that divides the signal into multiple components, and each component will carry a different frequency band. If you feel this is complex, say I have a filter which operates at 0 to 500 hertz, and since this is having a high bandwidth, what I can do is I can reduce, so this will be costly. So, I can reduce this to 5 filters each operating at 100 hertz bandwidth. So, this is taking care of 0 to 100 hertz, this is 100 to 200 hertz, this is 200 to 300 hertz, this is 300 to 400 hertz, this is 400 to 500 hertz. Kind of a divide and conquer approach, you can say. So, I am splitting the work into lot of smaller works, and each filter is responsible for a specific bandwidth. This is like a prism. White light is coming to the prism, hitting and splitting into different components, each responsible for a specific color. Now, this is a structure where I have this xn, and there are m such filters, each responsible for a small bandwidth. So, if it is a digital domain, so if 0 to pi is my like operating digital frequency, so you see that my overall filter, instead of working from 0 to pi, you can have sections which are pi by m. So, each filter will operate in this bandwidth 0 to pi by m. So, this is what you get. So, this is an example of a filter bank. Now, we see that there are downsamplers. Why we have used downsamplers? Because by the Nyquist theorem, we know that the sampling rate, the Nyquist sampling rate for proper reconstruction is twice the bandwidth. So, if the bandwidth is reduced to half, then I can reduce my Nyquist sampling rate to half. So, if the bandwidth is reduced to m times, I can reduce my filter sampling rate, not filter sampling rate, but the overall signal sampling rate to m times. So, this is an efficient implementation, and this is called a digital filter bank. So, it can either have a common input like this. Here I have a common input xn, this xn is common to all the filters of the filter bank, or a summed output, which I am going to show in the next slide. That filter banks can be categorized as two types, analysis bank or synthesis bank. So, the analysis bank will split the signal into several signals which have a lower sampling rate, whereas synthesis filter bank will take signals at lower sampling rate and then sum them to form an overall signal. And in this side and this side, the sampling rates are same, whereas since I have used 5 such components, so the sampling rates of each component will be fx by 5, considering this is a uniform filter bank. So, filter banks can be used for performing spectral analysis, because now I can clearly see small segments, and this is kind of a time frequency analysis, because I not only have signals at different time intervals, but also it is looking at small sections of frequencies. And signal synthesis, like I can combine a signal from the component signals. So, like Fourier, if I have a signal, periodic signal, I am splitting into its sinusoidal components. So, that becomes your analysis bank kind of a thing, whereas the reconstruction, the inverse series is you take all the components, you sum them and you make the signal. This is the synthesis filter bank. So, analysis bank, as I said, it will break down the signal into several frequency bands, and these are parallel filters. See, these are all parallel filters, whereas synthesis bank will reconstruct the original signals from the processed bands which are coming by summing them. So, it is basically a combination process. So, there are several types of filter banks, like uniform filter bank, which I said, like the DFT filter bank. So, it will analyze a specific region of frequencies, and if there are say n number of filters in the filter bank, then each will take care of pi by n frequency range in the digital domain. Then we have non-uniform filter banks where the frequency bandwidth of each band may be different, and these are often used in audio applications. And finally, we can have perfect reconstruction filter banks where we first split the signals x and then we reconstruct them into x hat, and these two should be same. Maybe there will be some phase lag because of some delays involved in the process, but overall the signal should be same. So, this x n and x hat n should be same or similar in some sense. So, that is it. Thank you so much. We will meet again in a new lecture.